In this video, we're going to take a look at a synchronous generator. I'll show you where it fits within the power system. We'll have a look at a 3D model of a synchronous generator, look at some of the various designs that you're likely to encounter, and I'll explain to you why we use synchronous generators to produce over 90% of the world's electrical power rather than asynchronous generators. If we take a look at this diagram here, you can see that the generator has been marked with a G and a circle around it, and it sits between an electrical transformer and a steam turbine. This is its position within an electrical power system. Electrical generators convert mechanical energy to electrical energy. The thing providing the mechanical energy is classified as a prime mover. The prime mover may be a steam turbine, gas turbine, hydro turbine, internal combustion engine, etc. The most important thing is that whatever energy we have at the start of the process, whether it be heat from steam or chemical energy from fuel, is that we're able to convert that energy efficiently and pass it on to our electrical generator. In the example shown here, we take the energy from fuel, we burn the fuel, we create heat, we pass that heat onto the steam, we transfer the heat again from the steam to the steam turbine, and the steam turbine converts that heat energy into mechanical energy. It's then the job of the generator to convert all of the mechanical energy, or as much as possible minus any losses we may have, into electrical energy or electrical power. Synchronous generators are used to do this. Over 90% of the world's electrical power is produced by synchronous generators. There is a very good reason for this, because synchronous generators have one big advantage over their counterparts, asynchronous generators. Synchronous generators are black start capable. They're able to start, come online and build their own grid. They don't need to connect to an existing electrical grid. A lot of wind turbines use asynchronous generators. They're called double-fed induction generators. It's a very special type of generator, and this type of generator can only connect to an existing power grid. So we need synchronous generators to build the grid in order that asynchronous generators can connect to it. That is the main reason why we use synchronous generators in the power generation industry a lot more than we use asynchronous generators. Now we know where a generator is installed within our power system, and we know why we're using a synchronous generator instead of an asynchronous generator. Let's take a look at a couple of examples of where a generator is installed within a power plant, and then we'll load a detailed 3D model showing all of its main components. Here is a coal-fired power station. If we take a cross section, we can take a look inside and we can find our generator. It's this item here. You can see the electrical connections that are coming out through these grey tubes. These connections are actually phases. There are 3 phases. We use 3-phase power with electrical generators because it allows us to get a lot more power out of the generator, about 1.5 times more power than is possible if we were using a single phase. And the other reason is that it's more economical for power distribution. Notice here that it connects to the steam turbine via the shaft and a coupling. And over this side, we've got our excitation system, and I'll explain to you exactly what that's doing a bit later in the video. Here's a slightly different type of power plant. This one is a nuclear power plant. Looks a bit like a Lego set, although it is a lot more complex, that much I can promise you. If we come over here, you can see that we've got our steam turbines here. These are low pressure steam turbines, and they connect again to our generator, which is this item here. In these examples, the generator is being driven by a steam turbine. That is very common. Thermal power stations produce the bulk of all of our electrical power needs. Coal-fired power stations, gas-fired power stations, oil-fired power stations, nuclear power stations, these are all types of thermal power station. If we follow the electrical connections as they come out, you can see that they go to an electrical transformer, this one here, and we'll send that electrical power into the grid via an open-air switchyard or substation. Now that we know where our synchronous generator fits within the system, let's have a look at a synchronous generator and all of its main parts. Here is a synchronous generator that you will typically see within a power station. This particular model took us a long time to make because it's quite complex. Just briefly, let's go through some of the parts. We've got the equipment we use for excitation within this little house. Then we've got a generator itself, whose primary parts consist of a stator and a rotor. This particular generator is long and cylindrical in shape. The reason being, the rotor inside is long and cylindrical in shape as well. You can have two main types of synchronous generator. One is the salient pole type and the other is the cylindrical type. Salient pole generators are used for large, slow-speed electrical generators. Hydroelectric turbines rotate at slow speeds, 50 RPM, 60 RPM, 100 RPM, 150, those kinds of speeds. Quite low when you consider that a steam turbine or gas turbine will rotate at thousands of RPM. The reason that you can't use salient pole generators at these high speeds is because of the centrifugal forces that act upon the rotor. Due to the high speeds, you want to keep the rotor within the generator as thin as possible. Centrifugal forces increase significantly the further away you go away from the point of rotation. So a long, thin generator rotor encounters far less operational stresses than if we had one that had a much larger diameter. Let's start by taking the generator apart and working from the inside out. We've got our rotor, which we briefly discussed. This is a long cylindrical piece forged from one piece of steel, and it runs through the center axis of our generator. We've got cooling fans, journals where our bearings sit, more fans here, also for cooling. We've got a retaining ring or clamping ring at this end that holds our rotor windings, or the rotor winding terminals I should say, together and helps them combat the centrifugal forces that they're going to encounter. And then we've got our windings, which are represented by these copper colours shown now. And these run from one end of the rotor to the other. This particular rotor is going to be either a 2-pole rotor or a 4-pole rotor. Notice we've got another clamping ring at this end, another fan, place for our bearing to sit, a coupling, etc. There's one bearing at each end of the shaft in order that we can support it. The types of bearings used for large generators are plain metal bearings, not roller bearings. Plain metal bearings are also known as white metal bearings, sliding bearings, and Babbitt metal bearings. So a lot of different names for the same thing. What's unusual about this particular rotor, and I'll mention it, although I'm guessing we're going to have to go back and correct this model slightly, is that there's this gap here, and the rotor surface itself is not perfectly smooth. Now, I'll tell you why I think this is a mistake. Firstly, I haven't seen a rotor like this with such large grooves. I have seen a rotor with quite small grooves, but nothing as pronounced as what's shown here. My general thoughts are though that because the rotor is rotating at such high speeds, these grooves are not desired. The rotor encounters resistance as it moves, as it rotates, and we want to minimize this. For this reason, I would expect the rotor surface to be smooth. However, I have not seen every type of generator rotor that's ever been designed, so I'm just trying to use my engineering powers of deduction here to figure out why it may have these grooves. One reason why it may have these grooves is to promote air flow or air circulation within the generator. A rotor will often be designed so that when it rotates, it creates some minor turbulence in order to promote cooling. Now, I mentioned air, but air is a cooling medium that's used only for smaller generators. The other type of cooling medium that you'll encounter is hydrogen. Originally, when they were building these generators, they used air. Then the generators got so large that they started to look for other cooling mediums. They found helium and hydrogen. Helium was quite hard to get hold of and cost a lot of money. Hydrogen is a lot easier to get and costs far less. That's why we have hydrogen-cooled generators, although for smaller generators you can also have air-cooled generators as well. Very large generators also use water cooling, specifically demineralized water. So keep that in mind. The three main types of cooling that you'll encounter when you're looking at large synchronous generators are air, hydrogen, and demineralized water. Let's stay on track though and have a look at some of the other parts. We can add our stator winding. The stator windings wrap around our rotor, and the gap between the stator windings and the rotor, which here is quite large, is called the air gap. The stator windings themselves need to be cooled, and this particular model uses water as the cooling medium. Notice that we've got the water manifold and then these water connections that come off here and connect to the stator bars or stator windings. The stator windings are quite interesting. They use conductive materials, mostly copper alloy, which is a mixture of copper and silver, but you can also use aluminium as well. The reason you don't use aluminium very often though is because aluminium requires a lot more space than copper, and we always want to keep our generator as small as possible. The design of the stator windings and rotor windings is also not so simple. The rotor is most likely cooled by air or hydrogen. The stator, air, hydrogen or water. We don't have solid copper bars that run through our stator. There are different designs to cool our stator and rotor. Sometimes we'll leave gaps between some of the components to allow air or hydrogen to flow through and cool our rotor or stator. Sometimes we'll leave passages within our conductor bars to allow the cooling medium to flow through. The conductor bars are made of different strands that are wrapped together to form a conductor bar. The reason we use this design is to reduce our losses and increase efficiency. While we're talking about losses, if I add the stator core, you can see that the stator core is also long and cylindrical in shape. The stator windings go into slots within our stator core, and the stator core itself consists of many thin laminate sheets of steel, cold rolled silica steel, that are pressed together to form a single core. Constructing the core in this manner allows us to reduce our eddy current losses and also our hysteresis losses. Keep in mind that the laminations will be very thin. A typical stator core may have 200,000 steel laminations that have been clamped together to form a single core. The rotor creates the permanent electromagnet that we need so that when the rotor rotates, that magnetic field cuts through our stator windings. We induce voltage within the stator windings, we close the circuit, and then we get current flow. So those are the two main parts of the generator, the rotor and the stator. This particular generator is hydrogen cooled, so we need things like a hydrogen cooler. The hydrogen itself is cooled by water. The water connects here, goes to a heat exchanger. The hydrogen flows across the heat exchanger, and that's how we cool it. We then reject the heat via the cooling water system to atmosphere if we're using a cooling tower, or to another system if we want to recapture the heat. We have other minor parts here, mostly to do with the sealing arrangement to stop hydrogen getting out of the generator. It's a closed pressurized system within the generator housing, which is why we need hydrogen seals to prevent any leakage. There will, however, always be some minor leakage, which is why a lot of plants have hydrogen cylinders and a bit of hydrogen gas stored on site. Very large plants may even have their own hydrogen generator. You can add the dust seal, bearings. Let's see, here is the one bearing and here is the other. Now we've got our end shields on the generator, oil deflector, press plate. Some of these are quite minor parts. And finally, we can add our frame, which sits within the main body of the generator. One thing that's missing here is the excitation system. Why do we need excitation? We need excitation because the rotor itself requires a DC voltage in order for it to become an electromagnet. So we provide DC voltage, and that allows our rotor to become a large electromagnet. This occurs because as current flows in one direction or the other, we get a resultant magnetic field around the conductor that it's flowing through. This will give our rotor a north and a south pole if it's a 2-pole rotor, or 2 north poles and 2 south poles if it's a 4-pole rotor. Cylindrical rotors that are used in thermal power stations are typically 2 or 4-pole only. The excitation system consists of some brushes. See, they've got handles on them here. The brushes are manufactured from carbon. We apply our DC voltage to the brushes. The brushes press against this copper surface here. These are our slip rings, and we pass the DC voltage to the slip rings, and this voltage then flows to our rotor windings. As you can see here, the voltage will enter, our DC voltage will enter from the brushes to the slip rings, and then through the rotor to the windings, and then we'll create our magnetic field around the rotor itself. Large synchronous generators normally use what's called brushless excitation. It's a type of excitation where you do not use brushes. So this one we're looking at now is a brushed excitation system. These have fallen out of favor a bit, and now I'll say you'll often encounter a brushless excitation system because the problem with the brushes is they're made of carbon. You have to replace the carbon brushes as they wear away. There's a lot of carbon dust that builds up in this area. That means more maintenance, reduced reliability, etc. We don't want any of that, so quite often now we'll use a brushless excitation system, which I won't go into detail, but essentially it means that the rotor itself has its own generator. It produces AC power. We convert that AC power to DC power using a rectifier, which is also mounted on the rotor. And then we pass that DC voltage to the rotor windings and produce our magnetic field around the rotor. So the big benefit there is that everything is mounted to the rotor, so there are no connections required externally to the rotor. As we see here, the reason we've got brushes and slip rings, etc., is because the rotor is rotating so quickly and we need to find a way to transfer that DC voltage from an external circuit to the rotor. That's quite difficult to do. Hence all of the brushes and the slip rings, etc. If we can mount that external excitation circuit to the rotor itself, then we get a lot of benefits. No slip rings, no brushes, and this is effectively what a brushless excitation system allows us to do. We're producing 3-phase power, although there are 6 connections here. This is because there are 3 phases going in, 3 phases coming out, and the generator is connected in star. So don't be fooled, this is not a 6-phase generator, it is a 3-phase generator. I hope you now understand why we use synchronous generators instead of asynchronous generators, where synchronous generators fit within an electrical power system, what the main components of a synchronous generator are, what the different cooling mediums are that you're likely to encounter, and how brushed and brushless excitation systems work. If you want to use any of the 3D models shown in this video, then head on over to saVRee.com. We've got over 400 engineering 3D models that you can use directly through a web browser in AR or VR. If you want to learn more about engineering, we've got over 45 hours of engineering video tutorials and courses at saVRee.com, and you can learn about valves, pumps, power stations, electrical transformers, and many other common engineering machines and processes. Before you go, don't forget to subscribe to the YouTube channel. Thank you very much for your time.